Okay, this is going to pick back up with Module 3, specifically at 3.5, which is reference models. And 351 is going to talk about the benefits of a layered model. So basically, so far we've seen the TCP/IP model, which is a 4-layered model. And we'll be learning about the OSI model down here shortly, which is a 7-layer model. So, first of all, why do we have layered models? Well, the very first bullet point says it's system protocol design. So basically, when we're doing something at the IP layer, for example, all we have to deal with is the internet protocols. When we're doing something at the transport layer, we just have to worry about TCP, the guaranteed delivery. When we're at the application layer, if we're doing web applications, we only have to worry about the protocols related to web applications. So it allows us to focus. Also, it says it allows competition, but it also allows protocols implemented by one vendor to work with another vendor, assuming they considered or looked at the same set of rules or same set of protocols. And then it gives a common language for us to talk about the capabilities. So over here at the right, we have the TCP model and we have the OSI model. So there were a couple of things that used to worry incoming Cisco students. One of them was having to correctly make Ethernet cables, and the other was memorizing the OSI model. So we'll go through and talk about the layers, but I'll go ahead and tell you a mnemonic device for remembering these. If you have 7 boxes, which you will have on your first test that says, oh, we'll put these in the right order, what you can do is you can remember the saying, please do not throw sausage pizza away. And if you go bottom to top and take the first letter, please do not throw sausage pizza away. You can at least get the first letter correct, and then hopefully having the first letter will allow you to, hopefully you remember the names of the layers and will allow you to get them in the right order. That's the mnemonic I use. There's one going top down. All people seem to need data processing. Of course, data processing is an ancient term for IT, but that's the way you can remember those. Now, they are closely related. When you want to recreate this diagram, the network layer, where you talk about IP, is the internet layer. The transport layer is the transport layer in both. In TCP/IP, we have what's called network access. In the OSI model, that's divided into the physical layer and the data link layer. In TCP/IP, we just have application. Over in the OSI model, sometimes these are grouped together and called the higher layers, but they're divided into session, presentation, and application in the case of the OSI model. So they took a very broad term, application stuff, and divided it into subcategories so that you get the benefits of the layer model. So we will talk about these down here in the next section. So I'm going to start at the bottom and go up. Physical layer is where we have physical things. We have wires. We have that which would be the media. We send electrical or light signals over those cables. It would also include the NIC card, the network interface card that's in our PC, where we would plug in a network connection. At the data link layer, we have the placing of frames onto media. At the network layer, we have information that allows one device to exchange information with another device. At the transport layer, we break the data into segments and we transfer that to the remote end. Then we reassemble that data and do some error checking. The session layer basically provides a service to the presentation layer to format or organize the data. Presentation is between the application and the session layer, and that is for the representation of the data. And the application layer is actually protocols related to the application. Again, like a web server would be HTTP or HTTPS, for example. The TCP/IP model, internet and transport are the same thing. Application is everything in layer 5, 6, and 7 of the OSI model grouped together. And the network access is the physical layer that has all the things that we talked about in the physical layer. Again, these are how they match up. I will probably give you 7 boxes on your midterm and ask you to put the layers in the correct order with the correct name. I may give you this diagram, maybe with the left side filled in, maybe totally blank, and ask you to fill in the OSI model and the TCP/IP model and show how they're interrelated to each other. Okay, 355 is a packet tracer that allows you to investigate the TCP/IP and the OSI models. I will be assigning that, so watch for that to appear in Blackboard. And we'll move on to data encapsulation, which we've talked about a little bit. So, segmenting messages is the breaking apart of messages. If we have a 20 meg picture that we need to send over the network, we're not going to send a 20 meg packet. We're going to break it into like 1K packets, a little over 1,000 bytes, and send that over there. So what that allows is that increases the speed of transmitting the data, and it increases efficiency. So if we have to retransmit, for an example, the amount of data we have to transmit is relatively minimal. The other thing that I'm not sure if they say here is if we were sending 20 meg packets, that means 2 machines would start communicating, and no other machines on the network could communicate until that 20 meg transfer took place. So by segmenting messages, it allows us to intertwine and send pieces of many messages between different sets of source and destination simultaneously. Not exactly simultaneously, but almost the same time on networks. So the segmentation is breaking a larger message into a series of smaller packets and sending those. And then multiplexing is the term for what I talked about here. We have 2 different individuals that are going to be communicating with the same server. And what it does is it allows the packets to be intertwined. Now, unfortunately, it looks like they're doing 1 for 1. Guy on top sends, girl on the bottom sends. Guy on top could send 1 packet, she could send 10, he could send 5, she could send 7, he could send 1, she could send 1, he could send 3, she could send 1. So they're just going to be intertwined with each other. It's not actually a 1 for 1 type thing. Each of these packets are going to be sequenced, which means they're labeled with a number. So they're sent 1, 2, 3. Hopefully they show up in the order 1, 2, 3 as separate message streams. This talks about protocol data units. This is what type of units we represent and talk about at each different layer. So down at the bottom layer, we talk about bits. At layer 2, we have frames. At layer 3, we have packets. At layer 4, we have segments. And then 5, 6, and 7 is data, data, data. So I would actually, if I ask you this, give you 7 boxes and expect you to go bits, frames, packets, segment, data, data, data. Because at the application layer, we're dealing with data. Here's another encapsulation example. Pretty much one that I think we saw before. We have a web page coming back from a web server. That is encapsulated into it's broken into segments. That segment is packed into an IP packet, and that IP packet is placed inside an Ethernet frame. And then the 1s and 0s that make up that frame are transmitted over the network from the source to the destination. De-encapsulation, I think we saw that. We have a bunch of ones and zeros coming into the client. It pulls out the Ethernet frame, checks it, rips off the Ethernet header and trailer, then passes it up to the IP layer that pulls off the IP header, passes it up to the TCP layer where the segment is looked at, and then the segments are placed together in the correct order to recreate the data, which in this case was an HTTP response, which would be passed to the web browser. So here's a check your understanding on encapsulation and de-encapsulation. You can do that on your own, and we'll move on to data access. So when we talk about addresses, we usually talk about source and destination IP addresses, and we might also include port numbers. So if we start up here, we have encoded data. We have destination and source addresses that are put in the TCP packet along with port numbers. It goes down to the network layer, which is where we have MAC addresses, which they're calling network addresses here. It then goes down to the data link layer, where it is packed into a frame. Here, when we talk about addresses, we're talking about IP addresses. Here, we're talking about MAC addresses or physical addresses. And then on the physical layer, we have timing and synchronization and data, a bunch of ones and zeros traveling over the network. So if we talk about layer 3 logical addresses, these are IP addresses. And from 111, you should know that an IP address is a 32-bit number. Guaranteed question on your midterm exam. 32 bits is 4 bytes. We take each byte, convert them to the decimal equivalent. We put periods between them, and that becomes known as the decimal dotted notation IP address. So here we're sending from 192.168.1.110 to 172.16.1.99. So that's the source and the destination. That packet is going to travel over the network. We haven't talked about routing yet, but the routers will get it to its next hop. And then finally, if the network's configured correctly and the machines are up, it will make it to its final destination. Here they're talking about the network portion and the host portion of an address. The MAC address, the subnet mask is what divides the network. But in this case, this network would be 192.168.1.0, and this would be 172.16.1.0 network. So we have a network portion that gets us to the right LAN, local area network. And then once we make it to that LAN, we have a unique number that identifies the host that the packet is destined for. We will do a lot of what's referred to as network math, which is where we use IP addresses and subnet mask and that type of thing to figure out network numbers and divide networks into smaller pieces called subnetting, etc. If we're on the same network, and I don't think they're real careful here, the same local area network, what we use is MAC addresses. So there's the same logical layer 3 network, which is what we're talking about, and now we're going to also add to that MAC addresses. So down here, with machines communicating with each other on the same network, that is from like a PC to an FTP server that's on the same network, or if the packet's going off the network, we have to send it from this PC to this router. What is used for communications on the local area network is the Ethernet address, MAC address, physical address, hardware address if I didn't say it. These are all ways to refer to this address. A MAC address is 48 bits. Again, probably guaranteed question on your midterm. That uniquely identifies the device to the local area network. The layer 3 IP address is an address that uniquely identifies the host. Unfortunately, they used private addresses here, so it would be on the same local area network as well. But if we were using public addresses, then we would say that this uniquely identifies the host in the world. So here they're showing that we have a IP address and a MAC address for each of the two machines that are relevant. Here they're showing the division between the network portion and host portion of the source. Likewise, network portion and host. So if the network portion is equal, like they are here, then we say that those two devices are on the same IP network, in particular the 192.168.1.0. The way we get that network number is by setting all the host bits to 0. And a lot of times we might see a network cloud at the edge of this router here that included all the devices that are in that network. If devices are on a remote network, that means they do not have the same network number, and we have to pass through a router to route that packet. So from the source, the first hop would be to the local router. So we would send a packet. Then the router would use routing information, its protocol, routing table, etc., to determine what the next hop would be. So here we have a topology that has a few more pieces of information in it. Like I said, if we were sending to this web server, which is off this one subnet over here, we would send it from here to here. The router would then determine, okay, the next hop is here, the next hop is here, and then this router would be able to get it to its final destination, which is the web server. And again, that's done because these devices are not on the same network. They do not have the same network portion. Okay, when we're sending, we have source and destination IPs. If PC1 was sending off the local area network, it would send it to the MAC address of all ones, or 11-11, etc. It would then rewrite the packet and it would send it out this interface. That would become the source. This would become the destination at the physical layer. At the network layer, PC1 and the web server are still the source and destination. So basically what it'll do is it'll rip off the data link portion, the Ethernet frame. So it'll de-encapsulate one level. Then it'll re-encapsulate so it can make it from this router to this router. This router would de-encapsulate to layer 3, and then based on the layer 3 information would re-encapsulate it with information going from this interface to interface. That process of de-encapsulating and re-encapsulating around layer 2 and layer 3 happens quite a bit as the packet travels through the network. Okay, so that's basically what this is showing you. So first host to router, here's what the packet looks like. Then when we're going router to router, this is what it looks like. And then finally when we're going router to server at the other end, this is what it looks like. So it's replacing the layer 2 information over and over again. Okay, Wireshark. Wireshark is another very important thing in this class. We, of course, been using Packet Tracer to do network simulations. We will be using Wireshark quite a bit. This is an application you install on your PC, and it is intended to monitor your actual network. But a lot of times they will give you Wireshark capture files that you can look at and ask you questions about it. So right here on the screen we see a couple of labs that I will be assigning. The first is fairly straightforward, going to the Wireshark website, downloading the appropriate version of Wireshark for your Windows, Mac, or Linux machine and installing it. And I'll probably, like I did with Packet Tracer, what you'll submit will just be a screen grab showing it running on your machine. Then I will turn around and assign lab 3710, which is then use Wireshark to view some network traffic. So watch for those two labs to appear on Blackboard. And then 3711, we have a check your understanding on the data access layer. And that finishes up this module. You can go through and read the list of the different things that you would have learned here. And then here's the module quiz down here at the bottom. So, 15 questions about the module as a whole. The other thing that I will send out soon is in the version 7 of the curriculum, which is what we're using. Instead of having an exam over each chapter, or using this current terminology, each module, we have what's called module group exams. And the first module group is modules 1, 2, and 3. So I've gone through and I've lectured on module 1, 2, and 3. Here in a bit, you will have all of your assignments for modules 1, 2, and 3. And then I will give you a date in the future, as well as information on how to take your first module group exam. So watch for that to appear, probably in your email, but possibly Blackboard as well when I make the actual assignment. That exam will be taken within netacad.com, and I definitely have information for that. So that finishes up Module 3. So watch for the related assignments in Blackboard.